Okay, to improve the utilization problem, what we can do is we could allow the sender to transmit more than one packet without waiting for acknowledgement for each packet. So as shown in this figure, so the sender first at time 0 send out a packet and immediately send the next, and it sends 3 packets in pipeline simultaneously. Technically, it's not simultaneously, but one after another, without waiting for acknowledgement of each packet. So immediately we can, this way will increase the utilization rate triple times. Right. So how does this pipelining affect the design of the RDT 3.0? You may want to pause the video and think about. So recall that in RDT, from RDT 2.2 and 3.0, we use a sequence number which is either 1 or 0 to ensure reliability. But in pipelining, we apparently every time we are sending out more than one packets. So only 1 and 0 for one packet is not enough. So we may need more sequence number or increase the sequence number for each packet in transit. And also both sender and receiver, they need to buffer the packets. At the sender, it needs to buffer all those packets that are sent out but not acknowledged. And so it is we need more complicated finite state machines. And a question here is, can we send unlimited or a large number of packets in pipeline? So actually, the experiments show that if we do not limit such the number of packets in pipeline, the communication performance will drop very quickly at a threshold after a certain point. We will discuss this later in detail when we learn flow control in TCP. And the answer is yes, we do need to limit the number of packets in the pipeline. And a popular solution is to use a protocol called go back N, so which we'll introduce next. So in the go back N protocol or GBN protocol, a sender can only send a maximum number of N packets, and these packets are on acknowledgement. So let's explain the idea given this figure. So this is the sequence of ascending packets. So we can divide this sequence into 4 different parts from left to right. So on the left, in dark blue, these packets are already sent and are already acknowledgement. The second part is those packets that have already been sent, but they have not been acknowledged. And the third part is those packets that we haven't planned to send, so they will be sent later after the packets have been acknowledged. And the last part, without any shadow color, is we do not have any plan to send, so it's not being usable. And we can use a number to differentiate these packets, starting from the one from here, which is the first packet that has been sent but not acknowledged yet. So we call this as the base. Now, all the numbers that lower than this base are packets that already acknowledged. We are more interested in the packet sequence number higher than base, and from the base to the one that had been sent but not acknowledged, we call these parts will be we call it packet in flight. Okay, and the next sequence number, this is the first packet that will need to be. This is the new packet that will be sent next. Okay, so the range of the permissible or allowable sequence numbers for the transmitted but not acknowledged packets can be viewed as a window size of n. So this is we limit the number of packets allowed based on RDT 3.0 is this size equals n. And as we are sending out packets, the window will sliding forward, and sometimes this protocol, GBN protocol, is also called a sliding window protocol. So GBN is the basis of TCP protocol. And recall that in RDT 3.0, we use a 1-bit sequence number, which is either 0 or 1. In GBN, we need more number of sequence number. Depending on how many bits we are using to represent the sequence number. And for standard TCP, it uses a 32-bit sequence number. So we have a sequence number from 0 to the power of k minus 1. And bear in mind that in TCP, the TCP sequence number is counting based on bytes rather than packets. So this sometimes we call TCP byte stream. Okay. So here is a state machine for the GBN protocol. Let's look at the state machine of GBN sender. So same is starting from receiving data from the upper application. By using and once it received a new data, it will call the function RDT send. Now here in GBN, the sender will first check to see if the window is full. So by window we are referring to the window size if this is full. Now in other words, we are looking at whether the number of unacknowledgement packets equals n, which is this light blue, if this number of packets equals n. Now, if the window is not full, then a packet will be created and sent. We will call this make packet. And if the sender will ignore this and does not send if the window is not full, a packet will be created and sent. Okay, and the upper otherwise, if the window is full, so that means, so in this case, the sender will ignore this message and does not send the packet. So usually what it does, the upper layer application will stop, will hold off and try again later, right? So if a sender receives an acknowledgement of packet which equals size of n, the GBN protocol will consider that all the previous or the older packets before this packet n, they have been correctly delivered to the receiver. And similarly, in RDT 3.0, GBN use a timer to recover the lost data as well as the lost acknowledgements in both directions. And whenever a timeout event occurs, the sender will retransmit any packets that have been previously sent but not yet acknowledged. Now, once all the packets have been sent and have been acknowledged, the timer will stop. And at the receiver, the GBN receiver will have, when it receives a packet with the sequence number n, and if it is in order, so if it has a sequence number that equals the expected sequence number, which means it's in order. So if you're sending a packet is 1, 2, 3, it should receive in sequence 1, 2, 3 as well. The receiver will send an acknowledgement of this n and finally deliver data to the upper layer. So this is the perfect situation. If it is the received packet is out of order, so the receiver will discard this packet and resend an acknowledgement in order to get the most recent packet that which is in order. We will also demonstrate this GBN protocol in Python in the seminar. Let's look at an example how GBN works between the sender and the receiver, and let's assume we have a window size n equals 4, and we sending 4 packets starting with sequence number starting from 0 to 3, right? So now at the beginning, the sender sends a packet with sequence number 0, and the receiver receives it and send an acknowledgement. And the next, the sender sends packet 1, and the receiver got it and acknowledge it. Now, the problem is the packet with sequence number 2 got lost, and obviously the receiver cannot get it, and the sender will keep forwarding, send the next packet and wait. Now the receiver receives the packet 3, however it will discard it, it does not use it, and sending acknowledgement of the previous packet, which is packet 2, because it is expecting in order packets, not out of order. And the sender keeps sliding forward, sending the next packet 4, but the receiver will again discard it and send the acknowledgement 1, which means expecting packet 2. And the sender sliding forward, again sending out packet 5, but because the receiver still expecting packet 2, and will discard it and send ACK1. Now, after the timer of packet 2 expire, the sender will resend packet 2. And luckily, if this time receiver have it, it will acknowledge it. Okay, so this is how GBN works. So in brief, if one of the 4 packets in this case got lost, the sender must wait for it to be acknowledged and before proceeding. So as each successive acknowledgement, for example, the acknowledgement 0 and acknowledgement 1, if they are received, the window will slide forward, and the sender can transmit 1 new packet, in this case packet 4 and packet 5 respectively. And on the receiver side, packet 2 is lost, and thus packet 3, 4, 5 are found to be out of order, and they will be discarded. Okay, so hope you have get understanding how a reliable transfer protocol can be designed. So it's all starting from when we look at the channel, whether it is reliable or unreliable. And for unreliable channel, like a bit error channel, it will cause packet error either be corrupted or lost. And normally the solution to recover from the unreliable transfer is to design a protocol called automatic repeat request, or ARQ. And we can implement ARQ at sender or receiver. We can use different features to support our design, and for example using a timer to detect loss, using acknowledgement or a not negative acknowledgement to indicate feedback, and using sequence number to support retransmissions. Okay. And for the ARQ, there are two different types. First is stop and wait. Recall that we have learned RDT 1.0. It's the most simple case for as a stop and wait protocol. But however, RDT 1 cannot deal with error in data channel. So we have RDT 2, which includes acknowledgement and negative acknowledgement. And unfortunately, RDT 2 cannot deal with failure in the feedback channel. So we have RDT 2.1, where we add sequence 0 and sequence 1. We also have a NUC-free version of RDT 2.1 called RDT 2.2. And again, unfortunately, RDT 2.2 cannot deal with packet loss. So we have RDT 3.0 by including timer. And then finally, we found out that RDT 3.0 is reliable, but it's not efficient. So that's why we designed pipeline sending to improve the utilization rate. So there are two typical solutions. One is go back N, which we have explained. The other is selective repeat, which is not covered in this lecture. If you have interest, you can go to the academic books. Okay, and you should, go back N is from the basis of TCP. So next we will go into more details about TCP, which is a fundamental protocol on internet. And when you look at those header fields in the TCP packet, it should make more sense to you why we need sequence number, acknowledgement number, and timer. Okay, so these variables, they were invented to use or inserted into the packet header in order to achieve the same target, which is a reliable transfer. So next, let's look at congestion control. So we assume that you have learned the basic idea of a TCP connection. If you haven't, so please you can read the academic book from Curious, which we have recommended as a reading list, in the reading list. So in TCP, first we will have a three-way handshake to establish a connection. And after the connection be set up, it will enter in the reliable data transfer, which relies on two mechanisms, congestion control and flow control. And we will cover the two in this lecture. And in the end, when the communication finishes, we will need to terminate the connection. And an interesting discussion is to think about why we need a three-way handshake, not two-way, when we establish a connection, and why do we need a four-way break, not three-way, when we terminate a connection. Okay. So here is a TCP header format, which is specified by the standard. You can find more detailed explanations in the RFC document. So here, let's analyze the header from the point of view of reliable data transfer. So we look at the sequence number. Recall that in RDT, we do rely on sequence number for stop and wait protocol and for pipelining protocol, and we do need acknowledgement for a reliable feedback channel. and we will learn how and the checksum is also the basic field that to detect packet error, and we will learn a new features the window, which is important for flow control. Okay. So in TCP, so by default TCP header has 20 bytes in total, and you can see there's no information of IP address because they were provided by the application layer. Okay, so next let's look at the TCP congestion control. So this is a protocol that developed in 1988 and by Van Jacobson. It's based on the AIMD algorithm, which we will introduce shortly. So the basic idea of TCP congestion control is to adjust the sending rate in response to congestion, and by congestion it means could be packet loss. So to control the sending rate, so TCP uses a variable called congestion window, which we will look at how this congestion, so it's a number. So how the value of congestion window changes along with the time. So in general, if a TCP sender detects no congestion, so it will increase the sending rate. If a TCP sender detects congestion, it will reduce the sending rate. So we will now look at how the congestion window size is increased and decreased, because the congestion window size is directly related with the sending rate. So on this figure here, it represents the severe congestion, which normally refer to when there's a packet loss. We call it, this is a severe, it is a serious congestion happened. So the first stage of TCP is called the slow start. As you can see, during this stage, the congestion window size increase exponentially. It's quickly, and the window size is increased by one maximum segment size every time when it receives an acknowledgement. And if at some point a timeout event occurs or timeout value expire, a packet, the congestion window will be reset to 1. So this is for a punishment of TCP, and then it will gradually increase again, but this time we're not going to the original higher value, we will go into a threshold. Okay. Just be carefully increase. You can see TCP, when it adjusts the congestion window, is quite conservative. Okay, and it will go into a congestion avoidance, which is linearly increase the window size. And if the timeout happens again, it will reset and increase start another slow start, but will reach at a lower threshold. Okay, so another situation is a lighter congestion status. So here at the beginning, the congestion window is have a slow start as well. If in this case we are not looking at timeouts but duplicate acknowledgement, if the sender receives 3 duplicate acknowledgements, that indicates that the network is going through congestions. Now, why is 3 duplicate packets? Now, for example, let's say a receiver expecting packet with sequence number 10, but it only received the sequence number 11, 12, and 13. So the receiver will send one acknowledgement packet for each of these the 3 packets. So therefore, the sender will receive 3 duplicate acknowledgements in order to have the in-order packet at the receiver. So if this happens, that means the network is congested, and the sender will enter a status called fast recovery. It will reduce the congestion window size, but not serious, not that hard as in the above case. It will go to a threshold, and then enter the congestion avoidance. And if the duplicate acknowledgement event occurs again, reduce, but this time it will reach a lower threshold and enter the congestion avoidance. Okay. So usually it is reset by half, not reset the congestion window by 1 for every duplicate acknowledgement event. So this bear in mind that the two the two figures, they are coexist in a single TCP connection. We separate into just to help you understand, because these are the reactions to two different events. So a key action in TCP congestion control is to determine the value of timeout, because it directly the timeout value here, because it directly changes the curve. And a straightforward way to measure the round trip time so in the standards, the timeout value is calculated based on the round trip time. And a straightforward way to measure the round trip time is, intuitive and naturally, we can measure it once, right? By using a pin, sending a pin packet, measure it's it's when it's sending out and received. So we can use this. Could be a clue for the round trip time. However, this is not accurate, because in real life, the round trip time is fluctuate frequently, in particularly when there is congestion. So it is suggested that when we estimate the round trip time, we follow the Jacobson-Karn algorithm, which is defined in a standard called RFC 6298. So the idea is every time, so when we observe a round trip time, so we will smooth it by combining the previous round trip time and the current measurement, and we give the previous one and the current one different weight. So in this case, we can have a good smooth value of round trip time in order to alleviate the fluctuation of the network condition. And we can also compute how deviates that our our sampled round trip time, it deviates from the smoothed value. And in the standard, it recommends that by using this equation, we can calculate the timeout, and this timeout will be used to determine how long it waits, when this timeout, this punishment on congestion window size should occur. Okay. So next, let's analyze the performance of TCP congestion. So in TCP, congestion control, it uses linear additive increase and exponential multiple decrease for the congestion window size, in short for AIMD. So why should we trust AIMD? Is it if we use it, how fire is it if there are multiple TCP flows? Because there is a chance that if we have many TCP sharing a bottleneck, some TCP flow will occupy most of the bandwidth, and others will starve, will have very little bandwidth. So this is not fire. So there is a research experiment showing that AIMD, and luckily it can well satisfy the fireness. So we can have a look. So this is let's assume we have two TCP, TCP1 and TCP2. So we so the x and the y axis are the throughput of the two TCP flows. So the optimal bandwidth share is the intersection between the two lines, the blue and the right. And the right line here represents the efficiency line. So below the right line, this is area where the network is underload, and above that is where network is overload, and on the line means the network is perfectly saturated, not too heavy, not too light. And the blue line is the fireness line. If the throughput is along the blue line, that means TCP1 and TCP2, they equally share the network bandwidth, right? And the target of control, of perfect control, is to bring the system to the optimal point, regardless of the starting position. No matter where we start, we should always converge to this intersection. So this is the best point that we have good throughput, we have good efficiency, and the utilization. So at point A, now this is where the sum of throughput of TCP1 and TCP2 is less than R. So here we use R to represent the bandwidth. So the system is underloaded at point A. So now, according to congestion control, the congestion window of TCP1 and 2 will increase linearly, which is a linear direction going toward point B. So at point B is where the sum throughput of TCP1 and TCP2 is more than the bandwidth R, and the system is overloaded. Now in this case, when it's overloaded or is congested, it will cause packet loss. And the congestion window of TCP1 and 2 will decrease by a factor of 2, which is multiplicative decrease. So it will be going down. And as the congestion window increase and decrease back and forth, the overall throughput will going through back and forth between the overloaded area and underloaded area. And eventually, experiments show that TCP1 and TCP2, they fluctuate along this optimal point and will reach to the intersection point somehow. And you may wonder why AIMD is the best policy, that it's the best trade-off between efficiency and the fireness. How about AIAD? How about we linearly increase and linearly decrease? How about we what if we multiplicative increase and multiplicative decrease? You can do a simulation or analytical results to prove that, and the results have have shown that AMD is the best among the four options. And another question is, if the RTT of TCP1 is smaller than TCP2, so which connection will grab more bandwidth? So you can think about the questions. And the answer is, in practice, if RTT of TCP1 is smaller, so that means it has a faster response in terms of congestion window, right? And it will grab the one with lower RTT will grab more bandwidth quickly. Okay, so next is about now we have discussed fairness, and is there a way to evaluate the level of fairness? And a very widely used metric is called Jeans Fairness Index, given by this equation, where the xi is the normalized throughput of a certain TCP flow. Assume we have more than one TCP flows sharing a bottleneck, and n is the number of connections, and this equation will calculate and provide a unique digital value. And if the system is completely fair between TCP flows, then all the flow will receive the same share. And if, let's say, one flow receives all the bandwidth, then this is totally unfair system. And if some flows receive, let's say if k flows receive 1 out of k bandwidth, and the remaining flows receive 0, and we can calculate the according fairness. So you can go to this research paper for more details regarding the Jeans Fairness Index. So this is a pretty straightforward equation.